Hello everyone! In this episode we're going to take a look at density again, but this time we're going to look at how to measure the density of objects that are not particularly regular in shape or are quite small but numerous in number. That way we can get the density of the material and work our way through. We're also going to take a look at how to use graphs effectively when measuring density, because sometimes you've got so much data that you just have to draw a graph. Alright, so let's just take a quick recap for those of you who have been away for a little while. The equation for density is equal to the mass divided by the volume of a particular material. The unit for density depends on the mass and the volume you are using. In today's lesson, we're going to use masses that are measured in grams, and we're going to use volumes that are measured in centimeters cubed. And now remember that centimeters cubed and the milliliter are exactly the same measurement, so we can use milliliter measuring cylinders and stuff like that. That means that if we're using mass in grams and volume in centimeters cubed, then we will get our density in grams per centimeter cubed, because it's grams divided by centimeters cubed. And that keeps our sides of the equation. Okay, the other equation that we're going to need to know for today is a general graph equation, and that is the equation for the gradient of a graph. The gradient of a graph is equal to the change in y divided by the change in x between any 2 points. Okay, sometimes you will see this written as the slope of the graph is equal to the rise divided by the run. Okay, that's a slightly simpler way of doing it. Okay, where the gradient is the slope, how steep the graph is. So if I have two axes like this, and I then draw a line on it, this line has a particular slope. And this line that I'm about to draw, this line here, has a less slope. So in order to measure their gradients, what I would need to do is I would need to pick 2 points on the line, ideally quite far apart, because that gives me a better answer. So there's 2 points there, 1 point there, 1 point there. And what I have to do is I have to find what is the change in y. So what is the change in the y-axis going from that point up to this point, and what is the change in x required to get across? So what are my y increase and my x increase or decrease to get from that point to that point? And then on the other graph, let's do that in blue. Let's pick this point here and say this point here, because it doesn't have to start at the start. Though if you can, you probably should start at the origin if you possibly can, but that's all right, we'll do it. And then we would want to find the change in y and x. It doesn't matter which way around you do it, x and y, just provided you put it into the calculation that it's change in y divided by change in x. Now, writing change in, or even rise and run, takes a little bit of time, it's a little bit annoying, and we want to look a bit fancy. So change in y can be written as capital delta, which is a little triangle, delta y, and then the change in x can be written as delta x. And I like doing it that way because it allows you to write it in quite short form. It also allows you to use Greek, which makes you seem really smart. The symbol for gradient is rather annoyingly m, for reasons that I'm not quite sure of, but I'm sure that the answer exists somewhere in Wikipedia. So we can write rapidly that m equals delta, that's better, delta x divided by delta y. Okay, that's the base information we need for today's lesson. Okay, so density equals mass divided by volume, and gradient equals change in y divided by change in x. All right, so let's take a look at a little object here. So let's imagine that I have some water in a measuring cylinder, and I've already measured the initial water level to be 25 milliliters, and I have some little bits of material sitting on a set of scales. I have 4 little balls here, and they have a combined mass of 12.21 grams. All right, so what we want to do is we want to find the volume of these, because we've already got the mass. We can write that straight up in the corner here. We can write the mass equals 12.21. We'll come back to that a little bit later. So what we need in order to find the density is we need the volume. Now, finding the volume of these little things mightn't be too bad. We could go and get some vernier calipers or something, get their diameter, use the equation of a sphere, but maybe they're not completely regular in shape. Okay, or maybe we're not particularly keen on doing the volume of a sphere, or maybe these things are very, very small and it would be very inaccurate for us to do so. Either way, let's find the volume a different way. Now, if these things sink in water or in any form of liquid, what we can do is we can use the displacement method. And that is that we can take our little objects and we can move them through the air and plonk them into some liquid. And what will happen is that our liquid level will rise up. That our liquid level started at, what was it, 21, if we run backward, 25 milliliters, and has gone up to 42 milliliters. So that's 25, the difference between 25 and 42, that's a difference of 17 milliliters. So we can now say that the mass was equal to 12.21 grams, and that the volume of this is equal to 17 milliliters, which is 17 centimeters cubed, as we're at extreme pains to tell you that milliliters and centimeters cubed are the same thing. So in this case, we can do density is equal to mass divided by volume. So the density D is equal to the mass, which was 12.21, divided by the volume, which was 17. And the density then is equal to 12.21 divided by 17. And our answer is 0.72 to 2 decimal places grams per centimeter cubed. Simple as that. Now, what you're likely to be asked to do is you're likely to be asked to explain that process. And that is that we take our object or series of objects, find their mass, not their weight, find their mass on some scales, then record that, place the things into water. Okay, first of all, measure your initial water level, place the things into the water gently because you don't want any splashing. Let the water level come up, find the final water level, find the difference between the two, and use density equals mass divided by volume. Okay, simple as that. Notice I didn't divide by 4 or anything here because I had the mass of 4 of them and the volume of 4 of them, so the density comes out as the density of the material. And that's really, really, really important. You're not actually finding the density of a particular ball or a particular object. You're finding the density of the material. So it doesn't matter if it's a huge amount of material or a small amount of material. You don't have to do anything other than that. Okay, try to think about it in this way. Like, why would you divide by 4 of these? Because each of these little spheres could be considered to be little half spheres, so why didn't you divide by 8? Or you could think of each individual atom in there as being a little ball. Why didn't you divide by several hundred squadillion? Because you don't need to, because you found the mass of 4 of them, and you found the volume of 4 of them, so you're finding the density of the material, because the 4's cancel top and bottom. Okay? All right, now let's imagine we do this lots and lots and lots and lots and lots. Then we could maybe have a full table of results. And let's imagine that we did it not just for little red spheres, maybe some blue spheres, green spheres, purple spheres. We could actually end up with a table of results that looks a little bit like this. That we controlled our mass, so we have 10 grams, 20 grams, 30 grams, 40 grams, 50 grams, and 60 grams of 4 materials, A, B, C, and D. And every time I got 10 grams, I plopped it into some water, and I got 6.7. And then when I had 20 grams, I got 12.7. And when I got 30 grams, I had 18.7. 40, I had 24, and so forth. But what I could do here is I could do density equals mass divided by volume for each of these. And I could get the density at 10 grams, 20 grams, 30 grams, 40 grams, 50 grams, 60 grams. They'll all be ever so slightly different because of experimental error. And then I could go 1, 2, 3, 4. There, I've got 6 results here. Excellent. So I could divide them by 6. So I can get 6 different densities, divide by 6, and get an average density. That seems like an awful lot of work to do. However, for all of these, that I would have to have the average density for A, the average density for B, C, and D. There must be a better way of doing this, especially because imagine in reality that if I was doing an analysis of a particular material, I might have maybe several hundred runs down here, and I really don't want to have to go through that process. And this is where graphing comes in handy. So what I'm going to do is I'm going to draw a graph. Now, normally you would expect to put mass across the bottom because it's our controlled variable, but we're not going to put mass across the bottom, we're going to put mass up the side. I'm going to explain that to you in just a second. We're going to put mass up the side in grams, and we're going to put volume across the bottom, and we're going to put the volume in centimeters cubed, just as it says in here. And hopefully what we're going to do is we're then going to plot all of our points like this, and we'll draw a line of best fit through them. Now, we know our line of best fit goes through the origin, Okay, so we can always start our graph at 0, 0. And that's something I strongly recommend you do because it will make calculations later really simple. Okay, do start at 0, 0 because it's sort of self-evident that an object that has no mass doesn't occupy space, so has no volume, and an object that doesn't occupy space doesn't exist and therefore can't have any mass. Okay, especially in the context of density. There may be some weird kind of waves and things like that there where you get into wave-particle duality. You can get nerdy on it, but we don't occupy space, we don't have mass. If we don't have mass, we can't occupy space. Simple. Okay, so 0, 0 is a point here, even though it doesn't appear on this. So we can, and we know that it's right, so we can force our line through it. All right, so we've got some data points that are not ideal, and we've got a line of best fit through that. How does that help me then with my density problem? Well, what I can do now is I can use the gradient of this line. Because if I go and get the gradient of this line, I pick a point here, and I should pick 0, 0 as a point, and I pick a point further away. Okay, and then I'm going to measure the change in y between these 2 points and the change in x between these 2 points. So my 2 points should be joined together by a right-angled triangle, like that. Okay, and this is my change in y, and this is my change in x. Okay, and my gradient then is equal to the change in y divided by the change in x. But my gradient is equal to, well, the change in y is simply the mass of the object. And my change in x is just the volume of the object. So my gradient is the mass divided by the volume. But the mass divided by the volume is the density. So if I draw my graph this way round, with mass up the side and volume across the bottom, then the gradient of my line will be the density. All right, so if we do actually go ahead and draw this and plot these points out, we end up with graphs that look like this. Okay, so we plot it all onto the same set of axes. So we've got material A is blue, material B is the orange line here, material C is the red line up here, and material D is a nice little purple one going through here, and they're all being forced through 0, 0. Okay, so what I want to do is I want to see if I can get the density of these materials just by getting the gradient of their line. So I'm going to move the graph across here to give myself a little bit of working out space, and I'm going to lock it into place so that I don't accidentally move it. I'm going to lock that. Okay, so what I need to do is I need to pick 2 points on my line to start with. So my first point is going to be 0, 0, but I'll do that for the first one. I'll maybe do an example where we don't use 0, 0 to show you that it still works. So there's my first point. Let's do this orange line. Okay. So what I want to do is I want to find a point that's on the trend line. So not this one, even though I've plotted this point. I ignore that entirely. My trend line is now the only thing I'm looking at, and I want to find a nice, easy one for me to measure. Okay. So I'm looking for maybe somewhere like that. Looks not too bad there. It's not quite exactly on the crossover, but it's pretty good. We can maybe have a go at that. Or maybe, yeah, this one here. Let's try this one. Okay, so we've got 2 lines, 2 dots. They're far-ish apart. I would prefer a bit further apart, but for the sake of simplicity, we're doing this one. We'll do a different one in a minute. So what I need to do is I need to find the change in y, change in x between these 2 points. Okay, so let's make that line a little bit thinner so that we can actually see what's going on. That's better. Okay, so this point here we've got axes, so we go 0, 2, 4, 6, 8, 10. Yeah, it's going up in 2s, so that's 12. So I can say that my delta x, so delta x is equal to 12, and my delta y is equal to, so I go from 0 up to 30. It's also got up in 2, so up to 32. Okay, so my gradient is equal to my change in y, 32, divided by my change in x, which is 12. So my gradient is equal to 32 divided by 12, which comes out as 2.6 recurring. So we'll call it 2.7 grams per centimeter cubed. Now, where did the grams per centimeter cubed come out of? Well, the change in Y is not 32, it's 32 grams. And the change in X is not 12, it is 12 centimeters cubed. Though we leave that out of the maths bit, because otherwise this all just gets really complicated looking. But it's 32 grams divided by 12 centimeters cubed, so therefore that's 2.7 when we do the numbers, and it's grams per centimeter cubed when we do our unit analysis. All right, let's try a different one. So we will do, let's take a look at the purple line, and we'll not necessarily start at 0, though I'm not entirely sure why you wouldn't, but let's start here, because that's a nice crossover point there, and oh, this is a beautiful looking line, so we'll go to here. All right, and we will grab ourselves a little red line between the two, and make sure the line style's nice and thin. So we're going to go all the way across to here, and then we stop, and then we go all the way up, because remember my 2 points have to be connected by a right-angled triangle. Okay, so let's take a look at what our delta y and delta x are here. So let's just delete this out, so we have space to put in our new information. So delta x to start with. So we start at 20, and we go across to 50, so delta x is a nice simple 30. And remember, it's 30 centimeters cubed, though we're not going to write that in. Delta y goes from 20 on the y-axis up to, again, 50 on the y-axis, so 20 up to 50. So that gives me a change in y, again, of 30. So that makes life nice and simple. So that's 30 divided by 30, which gives me a gradient of 1 gram per centimeter cubed. Easy as that, really. Easy as that. Now, the next thing to do then is, okay, so we've got all this information, we've got all this data, we've worked out what these materials are. Like this material here, material D, is probably water, because water at around about 20 degrees, around about 4 degrees or so, is 1 gram per centimeter cubed. So we've got a variety of materials here. What was the first one? It was 2.7. So 2.7 is round about the density of aluminium. 2.7 grams per centimeter cubed. So orange could be aluminium. Could be. Maybe it's something different, but it's likely if I've got a nice pure set of aluminium, I could be this graph here. Okay, so who cares? Who cares? Well, first of all, it gets you a nice, accurate value for the gradient. We've got a couple of little outliers here. So this little orange one's off the line. This little red one's off the line. We're not having to deal with those in our average. We're just ignoring them entirely and going bang straight through. So it gives us a better value than doing the average density. If there's a big outlier, we can just ignore it. There are no big outliers in this graph, but there are a couple of little random ones that are off the line. Next thing we want to do is we want to go, well, what happens if I get an unknown material? So let's try unknown material A, or unknown material 1. And it has a mass. Let's get ourselves an imaginary mass for our material. What are we thinking? So if we have an imaginary mass, let's say of 27 grams, okay, for our unknown material, and let's say it has a volume of 10 centimeters cubed. Well, because I've got a graph, I can actually just go and plot that point. So if I've got a mass of 27, there's 20, 2, 4, 6, 27 is halfway in between, and a volume of 10 puts this point here. And because that point is on the orange line, we can say that material is probably material B. All right, let's try unknown material. Let's try unknown material 2. Try a different one. Let's say it has a mass this time of 48 and a volume of 30. So mass of 48 grams, that is, and a volume of 30 centimeters cubed. And let's go and plot that point. So we'll get the black marker out for this one. So mass of 48, so we go up to 42, 4, 6, 48. And what do we say we had? We had a volume of 30. So there's 10, 20, 30. So that puts it bang on that line. So our unknown material 2 is actually material A. And we can use that to identify the various points. All right. Now, your turn. In the description below, you will find a link to a little worksheet that allows you to try this out. There's a couple of graphs to draw, a couple of gradients to calculate, some materials to identify from unknown stuff. Have a go at that. Let me know how you get on in the comments. Any questions, let me know. And before I forget, just before you go, always remember that physics rocks. It's true.